is defense. It's great to see you graduating. It's unbelievable to think that you just started 5 years ago. When you coincided with my first year, so I still remember when you came in and joined MIT. And so to think about the progress that you've made over the last few years is really remarkable, and we're going to get to see that today. So Daniel actually joined MIT from Cornell. He was a member of Natalie's research group, I guess, for your senior thesis. And came in, which Jen has mentioned is one of the great draws that you had to make him an offer and talking him into joining us here at MIT. So since that time, he's been a valued member of the graduate department here, and just found out won an AGU Student Award last year, and has put out a couple of really remarkable papers in his time since being here as well. And as reading through the thesis, realizing that there's a couple more to come. So he's gladly going to be staying with us. I saw Noel walk in, so he's going to be doing the postdoc, assuming that he defends successfully with Noel and Susan. We'll see if we can release him to your group coming up shortly. So just to remind you for the format of what's going to go on, there's going to be about a 45-minute presentation. If there's something very pressing, you are allowed to interrupt, but otherwise, if there are just general questions, please hold those to the end. The audience will be asked to provide questions at that point in time, so be really tough and hard at that point. The committee, of course, can ask questions at that point, but otherwise we'll reserve our questions after we have you guys leave after that question and answer, at which point we will continue to grill him for at least another hour or two. So I'm very happy to introduce Daniel to talk about fundamental aerosol-cloud interactions and the aerosol indirect effect on climate. Thank you.
Thanks, Dan, for the introduction. I'm going to reset my timer before I jump in. All right, so I'm really glad to be up here today to present and share some of my research from the past couple of years with you all. It is Halloween. I'm a little disappointed nobody's in costume, but you know, we can let that slide. Again, thanks to my committee for being here today. And with that being said, I'm just going to jump right in. So today I'm going to cover a couple different topics, but to get everything sort of started, I'm going to introduce some background and context material so we all start off on an even playing field. Then the first part of the talk is going to talk mostly about some of my work on parameterizations for aerosol activation. But the part after that, which focuses on the aerosol-cloud interactions and the indirect effect, is actually going to be the bulk of this talk. So it'll be a little bit different than my talk for the mass seminar about 2 months ago. And then finally, I'm going to summarize and hopefully leave you with some implications for really interesting and important future work. So that being said, let's jump right into the introduction. So just to make sure we're all starting with the correct same definitions and everything, I wanted to be sure that I take a moment and define the atmospheric aerosol. So I borrowed this definition here from the American Meteorological Society's philosophy. And essentially, aerosols are the mixtures of liquids and particles that are suspended in the gaseous part of our atmosphere. So aerosols constitute everything from particles like dust and sea salt, as well as the droplets and things like that. Now, to describe the aerosol, we generally talk about an aerosol size distribution. So what we do is we consider all the different sizes of particles we have, and we think about how many of the different sizes. Now, this figure right here on the right-hand side, which shows the size distribution, also shows this complicated network of physics and chemistry which interact with it. And I don't want to go through in detail all of those processes, but I want to emphasize that the aerosol is a really complicated thing to study. Just a few things that are important that you might want to think about. Some aerosol particles are formed through the nucleation of vapors and gases in the atmosphere that stitch themselves into larger molecules. Then an important process which also modifies the aerosol size distribution is collision and coalescence. So different particles can collide with each other and stick together. And when you account for all these different processes, you might end up dividing your aerosol into sort of 3 dominant modes: a sort of small nucleation mode, an accumulation mode where the sizes are such that they're not quite big enough to just spontaneously fall out of the atmosphere, so their settling velocity is not too large. But they're also, you know, maybe it's going to take something like rain or something to wash them out. Then there's also another interesting mode of very large particles, which might be mechanically generated, and these are your dusts and your sea salts and things like that. So why do we care about the aerosol? Well, I posted 2 pictures here to emphasize sort of at first glance. So on the right-hand side here is a picture that was taken in a smog event in Beijing. As you can see, you can barely see behind this woman in the foreground. There's some figures back there if you can make them out. So obviously aerosols play a critical role in changing the visibility in the atmosphere, and they're important for air quality. But they also have important effects on human health. And that's why the characters in this, or the people in this photo are wearing surgical masks. They don't ingest them. Aerosols can embed, or if they're large enough, they can embed in the sort of vascular tissue in your lungs and cause damage. So that's not necessarily going to be the focus on this talk, but it is going to be an important motivating factor to keep in mind for the future. Then if anybody is from the South like me, you're also familiar with another sort of insidious health side effect of aerosols. So this is a plant that's got a lot of pollen and stuff on its flowers there. And so if you're like me, this is a sign of misery. So aerosol has all sorts of interesting health effects. But today I'm going to talk about how aerosols interact with clouds and radiation. So I want to paint a picture of what this physical process looks like. On the left-hand side here, I've made a sketch of a cloud. And what this cloud is doing is it's reflecting some solar radiation back out to space. Now, the way that it does that is by having some sort of distribution of droplets of different sizes. And those droplets are related to the types and number of particles that are transporting or being entrained or sucked up into the cloud. So an easy or sort of an obvious question to ask would be, what happens if you change the number of aerosol particles that are actually making their way into this cloud? Well, I've sketched out what that might look like. If you hold all else constant, in particular if you keep the liquid water amount the same, then if you increase the number of particles, in general you're going to increase the droplet number, and all your droplets are going to be a smaller size. And the impact that this has on the optical properties of the cloud is it's going to make it more reflective back out to space. So this process and the radiative forcing that arises from this is what we might call the first indirect effect on climate. It's how the sort of perturbations to the number concentration of aerosol influence the albedo of clouds and how that influences climate. But this process sets up a whole chain of complicated microphysical processes which further act on the behavior of the clouds. So just to give two sort of broad overviews of them, if you have smaller particles, then in general precipitation processes will be less efficient. And so what this can do is it can suppress the formation of drizzle, and it can increase the liquid water content of clouds. And this can also increase the lifetime of the clouds. So if you sort of integrate over this effect over a cloud lifetime, those clouds would also have an important change in their radiative properties. So they basically reflect more radiation back out to space. On the other hand, if we think about other modes of convection, so if you think of thunderstorm or cumulonimbus, deep convection, there's been a lot of work that suggested that aerosol could invigorate those storms or that type of convection in certain regimes. And so that could have a bunch of different effects ranging from the lifetime of these clouds, the formation of ice in the anvils, and this can also have an attendant impact on the climate. And so to understand these effects in sort of the aggregate on the climate scale, I want to introduce this figure from the IPCC's fifth assessment report. I think you're kind of legally obligated if you're a climate scientist to refer back to this. It's our measurement of what we've done to change the climate system since 1750. So the first important bar to notice here is this bar associated with CO2. We've emitted greenhouse gases like CO2 and it has warmed the climate. And we understand with a pretty good degree of certainty just how much warming should be associated with that. On the other hand, compare the bar for CO2 down to these two bars for aerosols right here. On the first right here is what we call the aerosol direct radiative effect. So this is a measure how the changes in aerosols have changed the scattering and absorption of radiation since 1750. So there's this large cooling effect due to scattering, but also this potentially large warming effect to absorbing. And the balance of that is a relatively small radiative forcing. Maybe a little bit negative, but it's quite uncertain. On the other hand, there's this bar right underneath it, which is labeled cloud adjustments due to aerosols. And this is a measure of the radiative impact of those changes in cloud optical properties, which I talked about on the previous slide. And the important thing to take away from here is that there's a huge error bar, and we don't have a good idea of how to constrain it. To emphasize that point, I want to show the second figure from the IPCC AR5. On the left-hand panel, it's showing a scatter plot of the total aerosol forcing, so direct and indirect, from a bunch of different models as well as satellite data. And so you see there's this huge sort of spread in the models. They're all over the place. If you're just trying to analyze the scatter plot, there's not a lot of coherence. But if you break it down into just different groups of elements, so on the left-hand side, the right-hand side, if you just consider these sort of highlighted global models and then the highlighted satellite estimates, you get a slightly different picture. Satellite estimates tend to produce a smaller estimate of the indirect effect, and the global models produce a larger one. But it's been difficult to date to reconcile those differences. So as a result, we're left with this expert assessment on the far right-hand side, which is a great deal of uncertainty. So this is complicated, and it's hard to make progress on this because the indirect effect is this complicated sensitivity problem. So I borrowed this figure from Ken Carslaw's paper in 2013, so I think it's a really nice device for understanding how the indirect effect works. So what we're going to do is we're going to consider the changes in cloud condensation nuclei, so the number of particles that are good at creating clouds, to changes in anthropogenic emissions of sort of aerosol particles or precursor gases. And what we can do is we can convolve the relationship between these two, then how CCN relates to droplet number concentration, and then to the albedo, to come up with this estimate of how anthropogenic emissions influence climate through an indirect effect. The take home here is that if you start in a climate state that has potentially low anthropogenic emissions and a low cloud albedo, and you sort of make a unit increase in the emissions, it really depends on where you start in terms of the emission space, how big your indirect effect is going to be. So if you start in a very clean atmosphere with low albedo, the same change in a high sort of albedo atmosphere, cloud albedo, is going to have a very different indirect effect. And so if we were to sort of write this down analytically, we might decompose the indirect effect like I've done right here, and try to consider how changes in the aerosol cloud system at each one of these stages is going to imprint on the overall indirect effect. So that's sort of a bottoms-up process-based approach to understanding the indirect effect. But we can actually do sort of think our flipping on its head and consider the indirect effect as like an inverse problem. And so we can derive these really interesting top-down constraints on the indirect effect. And to show this, I borrowed this figure from Murphy et al. 2009. And it does essentially a budget accounting exercise to back out a good constraint on the indirect effect. So what they've done is they've computed estimates of the radiative forcing from different greenhouse gases since 1950. And then they've sort of chipped away at this, thinking about where energy goes in the climate system. And the way to think about this is how Donald Rumsfeld once famously described our nation's sort of national security assessments. Once you account for the known knowns, all you have left in your system are the known unknowns and those really pesky unknown unknowns. But for our purposes, we're going to assume that all the sort of unknown forcing in the climate system is being balanced out by aerosol effects. And so when you do this budget exercise, you start on the right-hand side here with this green curve, which is the sum total radiative forcing. And then we're just going to subtract out where we know radiative forcing is going. So there's been cooling due to stratospheric aerosols, and then there's been warming, which has led to an increase in outgoing radiation, and then also heat storage in the ocean and land. And even if there's uncertainties on these, they're much smaller than the uncertainty in the indirect effect. And so when you're left at the end of this exercise, you have this white chunk right here, which we call, or we can call a constraint on the direct and indirect effect, or sorry, forcing. And if you estimate that, it's about negative 1.1 watts per meter squared. And if you go take that a step further and you compare it to greenhouse gas forcing and warming, this should be masking about 50% of the radiative forcing due to increasing CO2 over the equivalent time period. So that's a lot. And that's important in the context of future climate change. So this figure here is from Levy et al. 2013, and it runs a hypothetical scenario for warming over the 21st century, where what they've done is they've done a standard warming scenario, this black curve right here, which assumes that aerosol are going to decrease over the next 80 years. On the other hand, they also ran a paired simulation with it, where they kept the aerosol emissions constant at their 2005 level, so there's no decrease in aerosol. And by the time you get to 2100 in these simulations, there's almost a degree of Celsius warming difference in the outcome of these simulations. And this is suggesting that in the future, as we reduce aerosol emissions, we're going to reduce the magnitude of the sort of applied indirect effect, and we're going to unmask a lot of warming that we should otherwise be experiencing based on the radiative balance from the 20th century. So this sort of is a critical motivator in deriving better constraints on the indirect effect, because this is just one model's estimate of it. You know, different models will produce a different amount of warming for the same sort of experiment. So we really need to understand this better if we want to assess future climate change. All right. So with that background in place, I want to share briefly sort of the three main overview topics or questions in my dissertation. So for the first part of my work, which is chapters 2 and 3, it focused on the representation of aerosol cloud interactions in global models and ways to improve them. And so I'm going to briefly cover that in just a second. But if you want to learn more about that, I have a paper out in the Journal of the Atmospheric Sciences. And just on Friday, we had a paper, a manuscript come out in Geoscientific Model Development Discussions. And I'd encourage you all to check those out if you're interested. Then once we did this, I started thinking about, well, how does this representation or this direct coupling between aerosol and clouds influence estimates of the indirect effect? That's the focus of chapter 4. And then finally, I follow that up with a series of analyses that are focused on how the sensitivity of aerosol-cloud interactions contributes to this intermodal uncertainty that we previously saw in the indirect effect. So with that said, I'm going to jump briefly in and show some of the key findings from my work on parameterizing aerosol activation. So some definitions are due. I know I've been throwing out activation here without actually defining it. So let's talk about this process where aerosol nucleate or activate and form cloud droplets. So I plotted here the case of a single aerosol particle. And what we can do is we can write down a set of equations that describe the equilibrium saturation vapor over the surface of the particle. And that's depicted by this curve here. Supersaturation is relative humidity of 100%. It's the relative humidity greater than 100% divided by 100. So in this environment right here, you're sort of oversaturated, relative humidity is greater than 100%, and then here it's drier. So if we start with a particle and we want to consider how water vapor is going to condense on it, this figure essentially gives us a schematic of how it's going to grow. So the important thing is that if the particle is in this left-hand regime right here, if its particle size is less than, its wet size is less than this critical size, then it's going to respond to changes in the environmental relative humidity. If the humidity goes up, it's going to grow. If it goes down, it's going to evaporate. But interesting things start to happen once we get to this sort of turning point here, which we call the critical point. And for particles that grow beyond this threshold, it's actually thermodynamically favorable for them to continue growing regardless of what happens in the environment. So if the supersaturation decreases once they grow past this, they're still going to continue to grow. And we call these particles activated. And particles that reach this size, or at this point we would call them proto-cloud droplets. So they're going to go on and form your nascent cloud droplet population. So that's the picture of one aerosol particle. But in the atmosphere, like I already showed you, there's this sort of massive size distribution of lots of different types of aerosols. So we have to consider systems of aerosol particles in sort of this more complicated picture. To do this, we use the device of parcel theory. So we imagine a bubble of gas, so called a parcel, and we're going to adiabatically lift it in the atmosphere. When we do that, well, in a sense, it's going to cool following the adiabatic lapse rate right here, as well as the sort of speed at which we're lifting it. As it cools, if we start with some amount of water vapor, we're eventually going to produce a supersaturation, like we saw in the previous slide. That just follows from Clausius-Clapeyron if we don't let the water vapor go anywhere. Once the supersaturation forms, particles are going to start to activate. They're going to start growing. And as they grow, condensation is going to release latent heat. And what's going to happen is there's this sort of competition between the heating and the cooling, which is going to dictate the development of a supersaturation profile. And so I built a process model that sort of solves these equations and can produce simulations of how a parcel and the aerosol in it grow during its ascent. So that's depicted on the left-hand side here for just an idealized scenario with some sulfate aerosol particles and some sea salt particles. So what happens is there's this characteristic maximum supersaturation that occurs. And where the supersaturation occurs, some really interesting things happen to the aerosol size distribution. This figure shows traces of sort of characteristic aerosol sizes as they grow. And there's this sort of split or bifurcation in the aerosol population that happens at the supersaturation maximum. All of the particles that are larger than this, or larger than a certain size at this point, grow into cloud droplets, and all the ones that aren't turn into haze. So that's still important to know because those haze particles can have different optical properties, but we really care about understanding those cloud droplets. And in order to sort of figure out the supersaturation maximum, well, I should say, if you know the supersaturation maximum, then presumably you could just make this decision about which aerosol are going to turn into droplets and which ones aren't. And that might be an easy thing to do. If you go into the parcel model and you sort of solve the equations for the supersaturation curve, you just get this simple equation right here. And so anybody can say the maximum is going to occur when ds dt equals 0, and then you just have to solve it. And when you do solve it, you get an equation that looks something like this. So again, here's this S max that we care about predicting. All is fine and dandy. It's just a coefficient, and it's also an upper limit of integration. And then you sit there and you spend a few months, looking through papers and applying mathematics to that, and you realize that's a really hard equation to solve. So what people do is they look for ways to simplify this, sort of break apart the integrals, apply empirical parameterization where possible. And the idea is to come up with a scheme that lets you predict this S max so that you can predict the number of cloud droplets. So I looked at this problem and I tried a bunch of different approaches, and I decided to try a new approach to solving this, which involved emulating my detailed parcel model. So what I did is I took the model that creates plots like this, and I came up with a statistical technique to sort of relate the inputs to the model to an output, namely the supersaturation maxima. And when I did that, I realized that I could train it really to really accurately reproduce the detailed process model. So the plot on the right-hand side here is just a scatter plot of running the same simulation or same input parameters through my parcel model and then my emulator based on it, and then comparing the supersaturation maxima that I get in both cases. And so there's very tight spread on the 1-1 line here, indicating that the emulator is reproducing the detailed model very accurately. The differentiating here is different updrafts, so it's applicable over a range of different updraft and input parameter speeds. So that's one thing, and like I mentioned, there are already schemes that exist or other ways to try to estimate this S-max and cloud droplet number concentration. So I was interested in comparing my scheme to other ones in the literature. And so what I did is I took the 10,000 samples that I ran on the previous slide, and I ran them through a bunch of different other activation schemes. So there are 2 from the literature here. And then I stratified the different simulations based on these different combinations of criteria. So I separated them into updraft speeds that were either light, moderate, or strong. Light here is basically less than 50 centimeters per second. Moderate is between that and a meter per second, and strong is anything greater than that. And then different pollution levels. So the clean and light pollution are all less than a few hundred particles per centimeter cubed. Moderate and heavy gets into thousands and 10,000. So it's very, very heavy pollution levels. And the point here is that these different points show the mean relative error in the activated fraction versus the detailed parcel model. And the point here is that the emulator reduces sort of the mean properties of the detailed parcel model very accurately. On the other hand, the different activation schemes from the literature sometimes have issues, particularly in the regimes with light updraft speeds and with strong pollution. Heavy pollution. And this has to do with some of the assumptions that go into them that make headway in simplifying the integral on the previous slide. A lot of them have to do with what are called the kinetic limitations on droplet growth. So for instance, particles don't instantaneously grow in response to a change in supersaturation in their environment. It takes a little bit of time. And effects like that have to sort of be assumed away in order to make headway on an analytical solution to the previous integral. And there are other effects that influence this as well. This was important. This motivated looking at sort of a more generalized formulation for the aerosol in a more complicated framework. So I also built emulators to simulate droplet activation for use in a global climate model, specifically an aerosol climate model, which I'll introduce in the next section. But this is just sort of the sort of take-home plot from this second paper, which compares the global distribution of the mean relative error and droplet number for my emulator, and then one scheme from the literature. And so the point here is that relative to my parcel model, this scheme is under-predicting droplet concentrations pretty much everywhere, but that's just simply because it's tuned to a different baseline. On the other hand, there's this interesting regional distribution in the bias of droplet number concentrations. Particularly, there's a land-ocean contrast. So in these regions, sort of in Africa and in the Middle East, where there's a much higher loading of desert dust, the activation schemes, at least my emulator, tends to under-predict the droplet concentration a little bit. But in sort of the remote oceans, it has sort of a positive bias. So this is important because these different distributions in the bias for the droplet number concentration say something about sort of the different influences of aerosol on different cloud regimes across the globe, and could be a source for uncertainty in the indirect effect. And so that's what we're sort of driving to with this line of research. So just to review the key findings from this parameterization section, most importantly, we developed a novel and efficient aerosol activation emulator, which can be used as a parameterization in global models. We did a large sensitivity analysis looking at what parameters were most influential in the activation. But the sort of take home from that, which I didn't show a figure of, but you can know, is that aerosol activation is very sensitive to the updraft variability and also the accumulation mode number concentration. And then finally, there's this potential underprediction or underestimate of droplet number concentration in polluted regimes. And of course, errors in droplet number concentration, like I showed, were larger for the weaker updrafts, which could be influential for model estimates of the indirect effect. Okay. So switching gears a little bit, or sort of building on this, now I want to think about how the different parameterizations I've studied and the representation of aerosol cloud interactions can influence the indirect effect. to frame this a little bit, I want to show this result from a paper by Hosa et al. 2009. So just to orient yourself on this plot, the y-axis is a metric of the indirect effect. It's the change in shortwave cloud forcing between two different aerosol emission scenarios. Then what they did in this work is they looked at two important tuning parameterizations in their model. So models that, say 5 to 10 years ago that didn't have detailed representation of aerosol cloud microphysics had this sort of pervasive problem that they predicted too few of cloud droplet numbers over the remote marine oceans. And one of the ways you can sort of get around that is by including a tuning parameterization in your model that simply limits how low those number concentrations can go. And so this study considered how is the indirect effect sensitive to different choices of those parameterization, or that tuning factor. So the x-axis here shows different values of the tuning parameters, or tuning factor. And you see this really strong linear relationship between the indirect effect and the sort of minimum permissible cloud droplet number concentration. The idea that's going on here is that if you have a model which is allowed to probe very low cloud droplet number concentration states, it has a very high aerosol susceptibility. So it's going back to that same curve by Aerosol et al. 2013. On the other hand, if you start out with a relatively high droplet number concentration, you sort of saturate out the albedo or the delta albedo, the response to the aerosol perturbation. So the problem is that this is kind of an unphysical tuning parameterization, or sorry, tuning factor. How would you decide, what the minimum cloud droplet number should be? Presumably it could be 0. It could be as low as, the number of particles that you have. But you have to know something about the particles to, improve upon this. And so what we've done in works since this, and really even in the 10 to 20 years before this, is we've included detailed representations of how the aerosol influenced the cloud droplet number, sort of the parameterizations that I previously showed. So what I'm interested in is how does other parameterizations, namely activation, influence the indirect effect in this way? So to get at this question a little bit, I put together a simple global modeling methodology where I'm looking at paired simulations of an aerosol climate model under two different emission scenarios, a pre-industrial and a present day. And to show the difference of these are just global average cloud condensation nuclei plot, so the number of particles that are good at creating cloud droplets. Then I've run these simulations with the same sort of cycle of fixed sea surface temperatures, and I've done 6-year simulations. And what this lets me do is it lets me sort of isolate the fast atmosphere and cloud response to the different emissions perturbations. And then I've run this same setup for 7 different activation schemes, as you can see here. It's not necessarily important which scheme is which, but I want to emphasize that what I'm basically doing is I'm changing this relationship between cloud droplet number and CCN in the models. So again, thinking about back to that Aerosol et al. 2013 curve, I'm changing the slope and the shape of one of those curves and seeing how it's affecting the albedo susceptibility. The global model that we're using is the MARC, which is a combination of our own two-moment mixing state resolving model of aerosols and the community Earth system model. And just briefly to show what's going on in this model, we simulate this complicated external and internal mixture of aerosols. So we have this external mixture of sulfate and carbon, but we also resolve these two modes, this mixed black carbon sulfate and this mixed organic carbon sulfate. And so what this lets us do is it lets us treat some of the aging of the aerosols and sort of a second dimension of the anthropogenic influence on the aerosol population. We also include dust and sea salt in our model, and we have a fully interactive sulfur dioxide chemistry. So we create sulfuric acid in the atmosphere, and we nucleate sulfate particles that go directly into these modes. And these modes are fully interactive with the radiation in the clouds. So they're scattering and absorbing radiation, and they're also serving as the nuclei for cloud droplet formation via my activation schemes. All right. So the first thing to look at in a modeling setup like this is just what is going on with this cloud droplet number concentration, which at the end of the day is sort of one of the things I care the most about. So what I've done here is I've compared the simulated cloud droplet number concentration versus a set of in situ observations that were compiled over the past 20 or 30 years. So I've deliberately left off the label for which activation scheme is which to make a few points. On the one hand, some of the activation schemes have this bias in regimes where there's large concentration of particles. So you see it's underpredicting. The x-axis in all these plots is the observed cloud droplet number, and the y is the simulated. So for instance, this scheme is just simply not capturing some of the variability in cloud droplet number for the upper end of this regime. On the other hand, the other two schemes don't have that problem, but all of the models generally simulate a lack of sensitivity in cloud droplet number in marine regimes. I want to make this point because this analysis here leaves out a really critical step, which is it's one thing to just compare the cloud droplet number concentration, but the cloud droplet number concentration is diagnosed from the aerosol. So underneath here, we would only ever expect the the model to match the observations if we were also doing a really good job of simulating the aerosol size distribution. And that ends up being a really difficult thing to do. It's very difficult to get large number of measurements for the total aerosol size distribution and then do sort of closure studies or understand droplet nucleation. And even in these simulations or observations where we just have cloud droplet number, you can see there aren't that many studies. So I've actually written down how many studies are actually plotted on this map and in this plot. So that's kind of a problem and something to keep in mind. We can also think about how the model is doing in simulating the present day conditions for other climate state variables. But I want to motivate and move towards the indirect effect. So I've shown just two zonal averages here. On the left-hand side is the aerosol optical depth, and on the right-hand side is the shortwave cloud forcing. And then there's a lot going on these plots, but to orient yourself, the black curve here is derived from satellite observations. So MODIS on the left and Ceres EVAF on the right. The different colored curves here are the zonal averages for each of the 7 different simulations that I did, so the different activation schemes. Then behind them in the shaded area, the gray with sort of the white hashing, those are different estimates from another set of modern aerosol climate models that ran a very similar set of experiments. This is just to see how our model performs in the sort of the grander scheme of other aerosol climate models. And so like I mentioned, there's this issue of understanding cloud droplet number concentrations when you don't necessarily have the exact representation of the aerosol size distribution. And that's sort of shown here. In the southern hemisphere, we're significantly underpredicting the aerosol optical depth. And part of that has to do with the simulation of sea salt in our model, so we don't simulate probably quite as much. But then also there's issues in understanding the uncertainty, or sorry, the certainty or the error in these observations themselves. And so combining the two is a very difficult process. On the other hand, if we look at radiation observations, it's a bit of a simpler picture. So all of the models generally capture the shape in the shortwave cloud radiative effect. And so what the shortwave cloud radiative effect is, it's usually diagnosed in our models by doing radiative calculations where there's clouds in the scene and then one where there's not, and then just coming up with the influence of the clouds. We also make a correction for the presence of aerosol above the clouds that could be scattering radiation. But the take home here is that not only are all the models generally capturing the same profile that the observations produce, but there's not a lot of variability in sort of changing the activation scheme and how it changes the magnitude of those shortwave cloud radiative effects. But if we zoom in on that, it ends up being that there's actually sort of a lot of interesting things going on. So on the left-hand side, both these pictures or figures are still the shortwave cloud radiative effect, but on the left is the difference between the present day and the pre-industrial, so between my paired simulations. And on the right is just, for the present day case, difference versus one of the activation schemes. And what you see here is that the sort of sensitivity to aerosol perturbation, the difference between the pre-industrial and the present day state, is pretty similar between all of the different simulations, but the base state is different. So some of the activation schemes, particularly the ones that are simulating much higher cloud droplet numbers, actually have a much stronger shortwave cloud radiative effect in the tropics and potentially in the mid-latitudes in the northern hemisphere as well. And just to orient yourself, this changes 5 to 10% of the zonal average in the shortwave cloud radiative effect. So it's actually a lot. And when we take sort of the global average over all of this, that gives us an estimate of what the indirect effect is. And I've plotted for you here estimates of the indirect effect for all the different activation schemes I've looked at. And there's this huge diversity, up to a 0.8 watt per meter squared difference in the diagnosed indirect effect just from changing the activation schemes. And so there's actually a lot going on in this plot to sort of provide a sanity check that what's going on is really in the shortwave clouds. I've also I've taken the liberty of decomposing the direct and indirect effect, which is this black bar here, into a direct component, which is the gold bars, a long wave component, which is the blue, and then just the shortwave cloud radiative effect. And so this makes a lot of sense what's going on. We're not really changing the aerosol between our 7 different activation schemes. Those are relatively the same, and as a result, the direct radiative forcing is about the same. On the other hand, we're also not really changing the long wave indirect effect, because really what we're changing is the cloud droplet number concentration. So the long wave effect is mostly the same in all these different models. We're really changing things through the activation is in the short wave here. And again, it's about 0.8 watt per meter squared which is pretty big. But to quantify pretty big, I want to put this in the context of historical estimates of the indirect effect. So this is adapted from that same scatter plot that I showed in the introduction, where I've taken IPCC estimates of the indirect effect, and I've plotted against them this collection of scatter plots using the Aerosol models that I was looking at, as well as the 7 different activation schemes. And so what this shows is that the spread in the indirect effect from the activation scheme alone in my simulations is almost as large as the intermodal spread going back to the AR5. So this is pointing out that this fundamental cloud droplet number concentration and aerosol relationship is contributing potentially a lot of uncertainty in these estimates and a lot of the spread. Okay. So just to recap a little bit what's going on in the intro here. So I used different activation schemes in our global model to diagnose the indirect effect. And I showed that there is a very large spread in the indirect effect that arises from them. And the spread is mostly due to a change in the cloud droplet number and initiating a lot of other or secondary processes which are also feeding back on the cloud droplet number concentration. And I didn't show it, and I'm going to circle back around to this point, but it ends up being that the simulated pre-industrial cloud droplet number concentration very strongly correlates with the strength of the indirect effect. And that's going to sort of motivate this last section of my talk here. So I've talked briefly so far, mentioning in sort of broad terms that I'm changing the cloud droplet number concentration and its sensitivity to the aerosol perturbation. But I want to actually pictorially or graphically illustrate what's going on with that. So I've adopted the curves sort of in the vein of the Carzal 2013 paper et al. Again, and I want to show this convolution between the CCN concentration and cloud droplet number and how it influences the relationship between cloud albedo and the aerosol emissions. So what I've sketched on here is sort of a hypothetical relationship that you might derive between the droplet number and the aerosol for an activation scheme A. And what you do, or when you sort of use this in a global model, you get a relationship between cloud albedo or the indirect effect and the aerosol emissions that looks something like this. But there's a few important things to know about this. For starters, we generally tune the present day to what observations we have. So there's some analysis that's going in to sort of trying to set the cloud albedo for the present day to match what it is based on observations. You know, it would make, ideally we would like our models to reproduce what we observe about the climate system, and this is one way that manifests. So when we estimate the indirect effect from this, we have to make sort of a subjective decision about what our pre-industrial aerosol emissions and background aerosol look like. And I sort of represented that with sort of shading on the x-axis here. But our indirect effect is essentially the area that we would draw if we sort of did this analysis right here. So it's the change in the cloud albedo versus the change in the aerosol emissions. What happens then if we change the character of this curve, if we use a different activation scheme? Well, just thinking about it one way, I've sort of sketched this curve here, which has a little bit of a steeper slope in the relationship between cloud droplet number and CCN for low CCN concentration, and then is much less sensitive in the high CCN regime. So how might this influence the cloud albedo? So again, I've sort of schematically drawn that. You know, if we fix this scheme so that it's reproducing the cloud albedo for the present day, then sort of our free parameter is this estimate of the cloud albedo in the pre-industrial state. And you can immediately imagine that the indirect effect for this model is going to be much smaller, even though we sort of have a much higher sort of cloud droplet number and aerosol sensitivity in the low CCN case and a smaller one in the high. And again, this curve right here is essentially this sensitivity term, which I'm going to call the Aerosol-Cloud interaction. So that's the relationship between droplet number and the aerosol. And again, the change in albedo on the right-hand side is an estimate of the indirect effect. So with that sort of device in the back of your head, I want to think more about these simulations of the present day and pre-industrial climate. So on this is the sort of same type of zonal average plot, but I've plotted the zonal averages of CCN on the right. And specifically, these are the differences between the pre-industrial and the present day. So what's going on is this anthropogenic emissions are dramatically increasing the CCN around sort of 30 degrees north, but predominantly in the northern hemisphere. And sort of attendant with that, in the same places where the aerosol emissions are going up, we see an increase in the cloud droplet number concentration. But that increase is very different between the different activation schemes. There's actually a factor of 2 to 3 difference in the zonal averages between the most sensitive scheme that I used and the least sensitive. And so again, this relationship is sort of our proxy for aerosol-cloud interactions. And obviously it's different between these different activation schemes. if we take the sort of analyses of that and look at the relationship between cloud droplet number and aerosol, we can actually regress that against the sort of strength of the indirect effect. And that's what I've shown on this plot right here. But I've done it two different ways. I've showed using aerosol optical depth as a proxy for the aerosol on the left, and CCN on the right, or the cloud condensation nuclei. And you get a pretty similar relationship, which is that there's a very uncertain relationship between the strength of this relationship over the land, but there's a strong negative one over the ocean in both cases. And it's stronger if you use the cloud condensation nuclei as your sort of aerosol reference. And so that's kind of important because I should mention that we can measure this for the present day climate. You know, we can take satellite observations of cloud droplet number and these aerosol properties and try to develop constraints on what this relationship should be. And one of the reasons that we do that is because we can try to use that to back out what our pre-industrial estimate of the cloud droplet number concentration should be. So if we do that, we might be able to reduce some of this uncertainty about the past climate state in our estimates of the indirect effect. So I've done something very simple here where I've derived those same relationships that I've used on the previous slide, and I've used them to sort of hindcast the pre-industrial cloud droplet number concentration from my different models. And so what I do is I compare that to the actual sort of prognostic cloud droplet number in the models. And when I compare them, I get these different distributions in the relative error of cloud droplet number. And the point here is that the sort of easy measurements that we can make, the relationship between cloud droplet number and aerosol optical depth, end up leading to a gross overestimate of the pre-industrial cloud droplet number concentration burden, especially over land, which is shown by this hashed brown curve there. Over ocean, the problem's not nearly as bad, but if we shift our thinking to sort of cloud condensation nuclei, which are more closely related to the activation process, we can actually come up with better constraints for the pre-industrial cloud droplet number. And then just to summarize this, this goes back to the point I showed on the sort of interim slide, so a little bit out of order. But if we look at that diagnosed pre-industrial number concentration, we regress that against the indirect effect, we come up with this kind of surprising relationship, which is that the pre-industrial cloud droplet number concentration very, very strongly predicts the strength of the indirect effect in our different simulations. In fact, these correlation coefficients that I've shown, when I break down my averages over land and ocean or the full globe, are much higher than actually if I regress the absolute change in the droplet number concentration. And so that's pointing out this key thing that it really matters what your pre-industrial climate state was and how the albedo susceptibility is in that particular regime. And unfortunately, that's a very difficult quantity to probe. You know, at best we can use this sort of analytical exercise like I showed, deriving aerosol-cloud interactions and sort of hindcasting, but we obviously don't have observations of the pre-industrial cloud droplet number, and so it's sort of this sort of epistemic uncertainty in our estimates. Okay, just to summarize these last few slides really quickly, just based on the last one, aerosol optical depth-based estimates of these aerosol-cloud interaction metrics really poorly constrain the pre-industrial climate. Using CCN has the possibility or the potential to improve that, but they're not very widely available, those estimates. They're very difficult to measure. And so there's this recent paper by Stier et al. 2016 that argues that sort of the aerosol optical depth approach and using that to figure out CCN might not be the most accurate. There's a lot of uncertainty in doing that. But if we had better in situ measurements of cloud condensation nuclei, then we could extend this approach and potentially reduce some of the uncertainty in the indirect effect. And like I showed, the characteristic aerosol cloud interaction that you get based on your physics schemes, and particularly activation, really play a role in setting your indirect effect. Okay, so my last few minutes here, I want to just summarize and provide some implications for future work. So going back to my breakdown of the thesis goals and questions, the first thing I asked is, can this representation of aerosol cloud interaction in global models be improved via this emulation of detailed process models? I'd like to argue, yes it can. I showed that by building emulators I can reduce the mean bias in cloud droplet number concentration, although there's still these regional biases which could be important for the indirect effect. I further asked, how does this direct coupling between aerosol and clouds influence the direct effect, or indirect effect? And then, like I showed, using the different activation schemes, I can essentially tune the indirect effect in our model to the degree of almost a full watt per meter squared, which is quite large, and it's as large as the spread seen in multi-model intercomparisons. And then finally, how does this metric of aerosol cloud interaction and as a sensitivity approach sort of contribute to the intermodal uncertainty and estimates of the indirect effect? Sort of the take home there is that this metric is a very strong predictor of the indirect effect over oceans. And so this is important because it suggests that we should continue measuring cloud and aerosol regimes sort of in the marine or remote marine ocean and using that information to validate and check the performance of global models. Okay. So thinking about towards the future, everything I've shown so far has been very process level. We're talking about particles nucleating cloud droplets and trying to fully describe the physics that goes into that. But like I showed, it's difficult to get measurements of all these sort of in situ cloud droplet number concentrations and the aerosol and the size distribution. And so there's been this push in our field recently to think about taking this view of emergent constraints on the indirect effect. What are other things that we could measure in the climate system that are influenced by droplet number concentration and aerosol that might be easier to measure, and which we might be able to derive or back out better constraints on the indirect effect. So this figure right here just comes from a recent paper by Feingold et al. And it shows this relationship between the total albedo and the cloud fraction for a scene of stratocumulus, which they simulated using large eddy simulations. And so they can write the total albedo, which is easy to measure with satellite data, and they decompose it into a contribution from the clouds. So there's a cloud albedo times a cloud fraction, and then a surface albedo. And the idea here is that these two terms themselves are influenced by the cloud condensation nuclei or the aerosol. So if we could develop constraints using this albedo data, which is itself influenced by the aerosol and the cloud properties, that might be provide a better way to back out constraints on aerosol cloud interactions that sort of side skirt this issue of all the uncertainty involved in the sort of the chain of the physics explicitly between the aerosol turning into particles turning into cloud droplets. But I would suggest that we should take this a step further and not necessarily focus only on the sort of dynamics of different cloud regimes and observations of them, but we should also consider climate scale constraints on the indirect effects, sort of back to that Murphy et al. 2009 approach. And so for instance, we could ask this question: how does the indirect effect imprint itself on sort of the larger scale circulation across the globe? And so Chen put out a paper last year which looked at some similar questions. And what I want to highlight is this result here, where what he's shown on the x-axis is latitude, and on the y is the zonal mean change in precipitation. And what he did is he looked at a large number of global models and he stratified them based on how well they capture aerosol cloud interactions. So there's this group 1 and this group 2, and the group 1 has detailed aerosol cloud interactions. Then what he did is he went into the observations and he sort of computed the pattern of the change in precipitation, which is this black curve right here. And then he's showing that the models that best reproduce this pattern are the ones that, that A, take into account greenhouse gas force, aerosols and greenhouse gas forcing, as well as have this detailed aerosol cloud interactions. And there have been other studies that have shown that if you include aerosol cloud interactions, you can derive better estimates of regional temperature trends and other sort of climate variables. And the idea here is that these climate level variables are more robust. We have more observations going back further in time. And so they might provide a sort of a more level platform for assessing or constraining the indirect effect. And so I think that's all I want to say about that. Sort of coming up on the end here, before I close and ask or take questions and comments from the audience, I just want to show a few acknowledgments. So I wasn't sure the best way to do this, or I collected a bunch of photographs that sort of I think are symbolic of the time, or my time here at MIT. And so I wouldn't be here today if it wasn't for the support of a very large number of different groups of people. First and foremost, all the people here in PAOC and the EAPS department, all the faculty and the students. There's too many people to call out and name individually, but you all have made the time here just an absolute blast, and I've learned so much from interacting with you. I've also had the privilege over the course of my PhD to work with large groups of students from across the country in both the Graduate Climate Conference and the AMS Student Conference. And I've learned so much about different fields of meteorology and oceanography and climate science from putting together these conferences and meeting people really from all over the world. I make a snarky comment in my dissertation thanking all the people that I've played music with over the past few years. if everybody remembers the payoff retreat slideshow or slide recap from a few years that had all the different violin statuses that I had and making fun of me. It's really true, but the music community here in Boston and Cambridge has kept me grounded over the past 5 years and always given me a place to retreat to and have fun. And then most importantly, I wouldn't be here without the love and support of my family who were able to join me today, and especially my girlfriend Shanae, my brother Matt, and my parents Art and Carol. So thank you all so much. And with that, I'm going to stop talking and take questions from the audience.
Since Daniel closed with acknowledgments, I forgot to mention at the start that it's the first acknowledgments in a thesis I've seen that are completely in Latin.
Oh, that's the old copy.
Oh, the old completely in Latin and quoting Cicero. Very, very impressive. So,
some more reason.
I'll still be suitably impressed by the old version. So with that, maybe we take questions from the crowd today.
Sure.
Is the so the emulator, is it more efficient than one of these other activation parameterizations? And if so, how much does that save you in addition to any benefits in accuracy?
Yeah, so that's a good question. So the emulator that I have is basically just a polynomial expansion. So it's very simple and straightforward to analyze at runtime. So relative to the two other schemes that I showed, it's a little bit slower than the Abdul Razak and Gant, which has a slightly similar or slightly simpler analytic formulation. The other scheme by Morales, Benincourt, and Ennis actually uses an iterative approach to solve that integrated differential equation. So it's on the order of 10 to 20 times slower. Yeah.
I have a number, but I'll just ask one here.
Sure.
Yeah, so I have a question about biases in the schemes, and you need to go back up quite a ways.
Not sliding, so I'm just going to do it manually. If you want to start.
Okay, hold on. So
is it this one or?
No. You compared the three different schemes. Is that it?
I think I know it's probably this one right here.
Yeah. Okay. So the Abdul-Razak and Gant clearly has a problem for heavy precipitation, and the emulator looks great. So then later on, you apply these schemes to the aerosol simulated by Mark, and can you show there? So you're not showing Abdul-Razak and Gant here, but you are showing the emulator as having problems. So this is the number activated or the droplet number?
This is the droplet number, and the mean relative error compared to the Russell model running the same.
Okay, but it's the number activated. It's not a fully interactive simulation.
Right.
Yeah. Okay. So why is the emulator showing bias for the clean conditions here when it didn't show that in your offline calculation?
Right. So part of that. Part of it has to do with that these are much more complicated aerosol size situations. So for instance, there's also the influence of giant CCN. It mostly has to do with this interplay of very low number concentration, but the few of them that you do have, there's a larger fraction of the giant CCN seesaw. So that's the major source of the misprediction.
Okay, so the previous comparison was for just like a single mode.
Yeah, sorry, I should have said that. This is just for idealized single log normal node.
Okay.
And then going here is the full multi-mode aerosol.
Okay.
Sure, Chris.
I've always thought that people looking at these kinds of problems should make more use of satellite-derived cloud droplet number concentrations, both as climatology and actually on a day-by-day basis. I saw you had a bunch of surface observations. You compared to satellite.
I do actually. I can throw up a plot really quickly to show you. So this is the same sort of idea, looking at comparisons using a modus-derived product. So this is a yet to be officially published version of the Bennertz et al. 2007. So what it does is it looks at the optical fields for modus. It employs an adiabatic cloud approximation to estimate the droplet number concentration. And so I've compared that and computed the relative error and droplet number for two different activation schemes right here. At the bottom is the emulator, and the top is that Morales Balboa. So it's the same as the two other global maps. The idea here is that even using these estimates of the droplet number concentration, the different activation schemes in our model tend to underpredict cloud droplet number. But it should be pointed out that these estimates here are highly uncertain. So the order of magnitude on the uncertainty in these is about 80 to 100 cloud droplets per centimeter cubed in these high pollution regions, and it's about half of the magnitude of the droplet number concentration elsewhere in the ocean. So it's really difficult to sort of constrain the droplet number using the satellite data, even using sort of cutting edge estimates. Anyone else? I saw a few from left-hand side. No one?
I guess
Sure.
jump in. So you were relating the struggles of trying to look at sensitivity to estimates of pre-industrial aerosol concentrations, but there have been large changes, and sometimes there are aerosols in recent times, at least regionally, for various reasons. The North Atlantic has kind of cleaned up, and places east of Asia probably have gotten worse. So there's an opportunity there to use those changes when the field programs conducted at various times during those changes.
Yeah, definitely. I think that sort of drives some of the point I guess I should have made on the going backwards.
I have to say I missed the first half.
That's okay.
I was teaching,
So that's a really important observation. So there's been a little bit of work in the literature that has used this sort of framing, which is saying instead of looking at the pre-industrial, let's do our first simulation, say like in 1970, and look at the contemporary decrease due to measures to clean up air pollution and stuff in the United States and Europe. There's one great paper by Wang et al. From JPL, which looks at how this influences sort of the circulation in different regions. So there's a lot of potential there, but even going back to 1970, we don't necessarily have all the best observations of the cloud properties, and particularly the cloud microphysical properties. So where I think using that data will be able to help us is if we shift our thinking to these more climate scale variables and less on the nitty-gritty microphysics, and then there might be opportunity there to sort of simulate the changes, validate our models with what observations we do have, which are still better than the pre-industrial, and then use those to try to constrain the indirect effect. But there's also a question of definition, which is it's kind of your sort of measuring stick is different if you're measuring the change in aerosols from 1970 to 2010 versus 1850 to 1970 or 2000. So, but I think those difficulties could probably be worked out. Tom.
I mean, if I was just looking at the Rinaldi's product, for example, short wave radiation, so I was wondering how much of the area is due to the slope of the activation for the droplet of the aerosol, and compared to how much area is due to, for example, misquantifying the updraft velocities?
Yeah, that's a really good question. So there's a whole host of other microphysical processes that influence the shortwave cloud forcing. Like you mentioned, this issue of the subgrid scale sort of variability in the updrafts for a given climate model grid cell are a really important driver of this. So in our model, we have a very simple way to estimate the sort of that variability. We take a characteristic velocity, which is related to the turbulent kinetic energy, so it's sort of a standard way to estimate that distribution. There are more sophisticated ways of taking into account the subgrid scale variability, like you could integrate over a PDF of the updraft speeds and stuff. But that's a very important source of uncertainty. I didn't quantify it in this study, but all these other processes could play a major role in influencing how the activation is exactly affecting the cloud droplet number.
Any other questions for Dan?
Sure, Dan.
So maybe I missed it earlier, but how is pre-industrial aerosols usually even estimated in the first place? Are you sort of drawing a curve through present day like you were doing before and sort of following that backward, or?
So this is coming up with better ways to estimate the pre-industrial aerosol burden is a very important research question. At least in my simulations, we're trusting that we have some estimate of the physics and chemistry and the representation in our global model. The idea is that if we supply it with the correct boundary conditions, so the emissions that we have, that might do a good job of giving a sort of a stable estimate of what the pre-industrial aerosol burden is. but developing better constraints on that. There's a lot of techniques out there. I didn't really cover them much in this research, so I don't have too much to say on that other than it's sort of an important open problem in developing these sort of proxy or empirical constraints on the pre-industrial aerosol.
Anyone else? All right. If not, let's thank Daniel.